An honor to be again here in your seminar. And hello everyone from Regensburg. It's a pleasure for me to talk today about the quasi-stationary Stokes flow by capillarity in the plane, and the talk is based on two joint works with my co-author Georg Prokert from TU Eindhoven. So the outline of the talk: first I will present the mathematical model, the governing equation, and then I will present the main result and some ideas of proof. So let's start with the beginning, the mathematical problem. We are in the plane in R2, and the entire plane is filled with two fluids. We have one fluid which is located in omega minus of t, and another fluid on top, omega plus of t. Both these domains are unbounded, and they are separated by a sharp interface, gamma t, which is a graph of a function f, which depends on time, t, and the horizontal variable x1. Okay, I hear somebody. Good.
No,
so,
it's okay. But okay.
The interface f moves with the flow, and it's unknown. And we assume that far away from the origin, the flow is almost stationary and the interface is almost flat. We use mu to denote the viscosities of the fluid. Sigma is a surface tension coefficient, so we allowed for surface tension effects at the free boundary between the fluids, but we neglect gravity. So the equation of motion are the quasi-stationary Stokes equation. So we have this equation where on the right, the time derivative of v plus minus is missing. Yeah? So this is a quasi-stationary Stokes flow. The fluids are incompressible, so the divergence of the velocity is zero. So v is always the velocity, and p is the pressure of the fluid. And this is are the equation in the bulk. And there are additional boundary conditions, which are the standard one. So let us begin first with introducing some notation, which I have written down here. So we have this boundary gamma or gamma of t. And let's say we have a function z, which is defined on R2 without gamma. Then here we have omega plus, and here we have omega minus, and then we denote by z plus the restriction of z to omega plus, and by z minus the restriction of z to omega minus. But also vice versa, if we have one function z plus in omega plus and one z minus in omega minus, we define the function z on R2 without gamma by simply z is z plus in omega plus and z minus in omega minus. And if we have a point on x on gamma, the square bracket of z at x is simply the jump where we consider first the limit of z plus in x, if this limit exists, and then we subtract the limit of z minus in x. So the square bracket of z measures the jump of the quantity z across gamma. So to the boundary conditions, the velocity field is assumed continuous on gamma, across gamma, and then we have this standard boundary condition which says that the jump of the stress tensor T mu in normal direction is exactly minus sigma. This is the surface tension coefficient. Kappa is a curvature, and nu is the outward unit normal at gamma. So nu points always in into omega plus. Okay, and here you have the formula for the stress tensor. We all have also far-field boundary conditions saying that the flow is almost stationary far away from the origin, so f is flat and v and p are asymptotically zero. And finally, the motion of the interface is given by the kinematic boundary condition, which is this equation which says that the normal velocity cap v of gamma equals the normal velocity of the fluids on the interface. So remember, the fluids are equal, so we have only one on gamma, so we have only one equation here. And here are the equation of motion, which I have written before, and this equation should hold for positive time, and the interface F naught is assumed to be known at time t equals 0. So this is a moving boundary problem because not only V and P are unknown, but also the function F, which parameterizes gamma of t. As a result, the problem is nonlinear, but because of this curvature term here, which is, as you know, F double prime over 1 plus F prime square to the power 3/2. This curvature term is quasi-linear because it's linear with respect to the second derivative of F, and for if the interface is sufficiently regular, then also the whole problem is quasi-linear. I will refer very often only to F as being the solution because, and this is a strategy how to prove well-posedness, what we do is we solve the first 6 equations, and we will do this in a minute. And we will show that if we know F, then V and P, okay, there's a question in the chat. Okay. I will send you the slides after the talk. So we have V and P, we determine them as functions of F. And not that only that we say that these equations are for given F uniquely solvable, but we also represent V and P in terms of singular integral operators. And having done this, then we plug this expression in the kinematic boundary condition, the last equation, and we arrive at an equation only for F, an evolution equation for F, which we then solve by parabolic theory. And when solving these 6 equations for V and P for given F, we take advantage of the observation that these equations are all linear PDEs with respect to V and P with constant coefficients. And they are posed on the entire R2. And then one can use potential theory to solve this equation under quite lower optimal regularity assumption on F. So there is a lot of literature on the Stokes problem, but the quasi-stationary Stokes problem is less studied. And in fact, I only have these 4 references or 5, which I would like to mention. So Günther and Prokert consider the problem in 97 in arbitrary space dimension for HK initial data where K is larger than 3 plus n plus 1/2, where n is the dimension of the interface. 2 years later, Solonikov has considered the problem for C3 plus alpha initial data in 3D. And Friedman and Reitig, they have 2 papers in 2002, where they considered the problem in 2D for H5 initial data and in 3D for H6 initial data. So these first 3 references, they do not consider our setting. They consider a bounded geometry and omega t and one phase. So one has omega t, a bounded fluid and blob, and then this is a geometry they consider. And the Pruss and Simonet in their recent monography, they consider the 2-phase problem where they have an additional fluid which is surrounding this one. So let's say this is omega minus and this is omega plus. The exterior boundary is fixed and only gamma t is a boundary in between. And they consider the problem in arbitrary space dimension for initial data in the space WP2 plus mu minus 2 over p, where p is between 1 and infinity, and mu is larger than n plus 1 over p and less than 1. So you see in dimension, if n is 1, then mu should be larger than 2 over p. So, and is less than 1. So p equal to is not allowed. in all these references, the phase space is always embedded in C2. Yeah, this is what one may easily check that this is true. But with respect to the quasi-stationary Stokes flow, if F is a solution, then also the following rescaled function F lambda, defined by this formula, is a solution for each lambda positive. And this scaling invariance identifies in 2D, so in our setting, the space H3½ of R as a critical space. So the critical space is H3½ for this problem. And our goal was to establish well-posedness in the subcritical spaces HS of R with S between 3½ and 2, arbitrarily close to 3½. Because we have low regularity, the first drawback is that the curvature operator is no longer a function, but it can be represented as a derivative of a function because, as you know, this is F prime over omega prime, where omega is this nonlinear function with respect to F prime. So this is a simple observation, which is very useful. And for the analysis of the curvature is no longer is a distribution now for F in HS. And this is a problem. Moreover, however, with respect to the analysis, let me point out we have this term K nu, which appears in the jump condition for the stress. Now, if we multiply it with this function omega, then this is a crucial in observation. This term is a derivative of a function g, and g has two components, g1, g2, and both are fully nonlinear with respect to f prime. So they depend only on f prime, and they are given by this expression. So they are fully nonlinear. G is a fully nonlinear operator of f prime. And this is a function which will appear in our model. So we won't have the curvature term, we will have this function g, g1 and g2, which appear at the end when we have reformulated the problem. And for this case, because of this, we will treat the quasi-stationary Stokes flow as a fully nonlinear problem. And now to the main result. So we have two results. The first is from 2020, where we consider the case where of equal viscosities, and then we have a result from 2021, where we consider the general case when the viscosities are arbitrary. So in both cases, we establish the following result: S is between 3½ and 2 arbitrary, and then the problem is well posed in HS, meaning that if F0 is in HS, arbitrary, the problem has a unique maximal solution, FDP, such that F is continuous into HS, and the problem has order 1, so the time derivative is C1 into HS minus 1. The velocity is C2 in the fluid domain, in fact, it's C infinity, and is C1 up to the boundary. And the pressure is C infinity in the fluid domain and is continuous up to the boundary for positive time, and the trace of the velocity on gamma is h2 for each positive time, where t plus is, as usual, the maximal existence time, and we have also a result about continuous dependence of the solution on the data. Now, the parabolic, we have also established parabolic smoothing. For positive times, the function f is smooth as a function of t and psi, and the function f is smooth from 0 t plus into hk for each k in n. So in particular, f of t belongs to h2 of r for each t positive. And because of this property, our solutions solve the problem in a classical sense, pointwise. Moreover, we have a criterion which says that if we can bound the HS norm of f on each interval 0 capital T intersected with the definition domain of the solution, then the solution is global. T plus is infinite. So this is the result, and now I will give some ideas of proof and what can be done and what we did. So when dealing with moving boundary problems, the usual approach is to transform the problem on a fixed domain, or by using either Hanzava transformation or Lagrangian coordinates. So let me talk about the Hanzava transformation, which is something which I know from my research. So what one does in this case, one assumes that the fluid blob is the boundary of the fluid blob is parameterized by a function rho, which measures the sign distance from of a point x, which is located on a priori given smooth boundary psi of a domain omega to the fluid domain. So one assumes that the boundary of the fluid domain is the graph of the sign distance rho on sigma. And then if rho is sufficiently regular and smooth, one defines the so-called Hanzava diffeomorphism, which maps this fixed smooth manifold omega, domain omega, into the fluid domain omega of t. And then one pulls back the equation on a fixed domain omega. So the new unknowns are the function rho, the sign distance function, and the pullback variable, the pullback velocity and the pullback pressure. The advantage of doing this is that at the end one has equation on a fixed domain, which is very useful. However, this transformation transforms not only domains, but also the operators acting on the domain. So here we have delta. The Laplace operator will change to an elliptic operator which has coefficient depending on rho, nonlinearly. And then one has to solve the transformed Stokes problem, and one obtains solution operator for the pullback velocity and pullback pressure, which depend in an intricate way on rho, because the coefficient depend of the operators depend nonlinearly on rho. However, at the end, one obtains a nonlinear and nonlocal evolution equation, which can be solved. So to summarize again, so this solution involves solution operators to rho-dependent equations. In an unbounded geometry, these solution operators are difficult to handle, and they are defined under quite restrictive regularity and smallness assumption on rho. The alternative approach, which we consider because the problem is defining the full space, is to use potential theory to determine V and P explicitly in terms of F via an integral representation. And this is something which appears first in this paper of Badia and Duchon, where they consider the problem with equal viscosity 98. Yes. And this is something which was used quite recently a lot in the study of the Muscat problem. So the advantage is that at the end, one obtains again an evolution equation for the interface F. And I will show in a minute how one comes to this equation. But this operator on the right is defined explicitly in terms of singular integral operators, and it requires less regularity and smallness and no smallness assumption on F. So I will now point out how to obtain this evolution equation. And the first step is, as I said before, to solve the boundary value problem for the quasi-stationary Stokes equations. And the result is obtained together with Georg Prokert. F is in H3. So we need at this point that F, the interface between the fluids, is H3 function, and it's assumed to be given. And then the theorem said that the boundary value problem for the Stokes equation has a unique solution, Vp, such that mu plus minus mu minus multiplied with the trace of the velocity on gamma is an H2 function. So if the viscosities are equal, there's no such set, so there's no condition. This condition is needed only when the viscosities are different. The proof is technical, but the theorem says something more, namely not only that we have a unique solution, the solution is determined explicitly in terms of contour integrals. And now I will show you how to derive this explicit formula for V, because this is what appears in the kinematic boundary condition. Yeah. And when we know what the trace of V on gamma is, then we have reformulated the problem as an evolution problem for F. So I will give some detail in the case when the viscosities are equal and they are assumed to be mu. So now what we do here, we have gamma, we have V plus above and V minus below, and also P plus and P minus. We've used this as function on entire R2 without gamma. So V is defined on R2 without gamma, and P is defined also on R2 without gamma. And then we use the Stokes formula to compute that in distributional sense, so in d prime of R2, this distribution is given by this expression. So we have here the term, which is a term from the boundary condition on the stretch jump. And here, this is a Dirac mass on gamma. So this distribution is supported on gamma, and we have an explicit formula for it. And this is good news because the Stokes equation in R2 have fundamental solutions, two fundamental solutions, which can be found in the book of Ladizhenskaya from 1963. We have U is a velocity, P is a pressure, and the pressure is defined by this formula, which is nice. The velocity, we have a nice term, and we have this logarithm term, which makes problems, and that's why this computation are only formal. So because we know what this distribution is, and we know for the fundamental solution, then V is simply the convolution of the fundamental solution with the distribution F, and the same for P. And the formula for V is this one, so we integrate over R2 UKX minus Y FK, but remember FK is supported on gamma, so in fact we have only the integral of on gamma of sigma K nu K. If we write this equation of R, it appears now this term omega, yes? And omega K nu, remember, this is G prime. And this is what we use now. So instead of omega K nu K, we have GK prime. And now we integrate once partially with respect to S. And we put the derivative on this term. And we have here GK of S. Everything here is formal, but for F in H3, this formula is perfectly meaningful because when we differentiate with respect to S here, we get rid of the logarithm. And then we have a meaningful expression, and also for P, we have a meaningful expression. And then here is where actually the proof starts. So we prove that we define V and P by these two formulas, and we prove that they are solution to the boundary value problem. And here one has to use also some complex analysis, Playmate formula to compute traces of function on gamma. And remember, we need the trace of V plus minus on gamma in the kinematic boundary condition. And this trace can be determined by using Playmate formula time. And it can be expressed in terms of certain singular integral operators, BNMO, which were introduced by me in two papers in the context of the Muscat problem. And I will come a bit later back to what these operators are. But here you have on the next slide what the traces are, namely V1 and V2. The trace on gamma is defined. You have here a lot the singular integral operator, which all depend on F. And here we do not have the curvature, we have the function G. Yes, which is fully nonlinear with respect to F prime. And remember, And then we have the kinematic boundary condition, and then if from this kinematic boundary condition we obtain an evolution equation for f, namely dtf is an operator cal f applied at f, and cal f is simply minus f prime v1 plus v2, and you see here everything is explicit with respect to f. Yeah, so the right hand side depends only on f. And an important observation is we solve the boundary value problem for the Stokes equation for f in H3. But these formulas are well defined for f in Hs with s larger than 3/2. So this equation is meaningful for f in Hs. And then we will solve it for f in Hs. And at the end, we prove this parabolic smoothing that in fact the solution f is smooth for positive time in any Sobolev space Hk of R. Now, the formulation when mu plus is not equal to mu minus, to obtain it is a bit more difficult, more involved, but one obtains again a similar formula. So dtf is equal mat-cal of f applied of f, where here we have this expression. So before we had here v1 and here we had v2 on gamma. Now here we have a new operator which depends on f, and this dependence is more complex. Namely, beta has to be determined as a unique solution to this equation. And here d of f is a double layer potential for the Stokes equation and the graph gamma, and it's given by this formula. So again, it is expressed by this using these BNMO operators I mentioned before. A mu is this quotient, and v1, v2, this is not the velocity in this case, but these are simply these two formulas. So the right-hand side is known, explicit in terms of f, and then we have to invert this operator and then determine the beta as a function of f. So if the viscosities are equal, then this term is not here, and beta is simply this term. Now here we have a 0, but we simplify the 0 with this one, and you see then that beta 1 will be v1 and beta 2 will be v2. So formally, if we put the viscosities equal, we obtain the previous formulation. So this case of different viscosities is more involved because we have to solve this additional equation for beta, which induces additional nonlinearities and non-localities. And the invertibility of this operator is shown by using some underlying Rayleigh formulas and for the Stokes equation. And here we were inspired by a paper of Chang and Pak from 2009, where they consider the problem in a bounded domain. So our argument, we are here in an unbounded domain, so the setting is different and the arguments are a bit more complicated. But we also use underlying Rayleigh formulas for the Muscat problem. But having inverted this operator, then at the end we have to solve in both cases this fully nonlinear evolution equation, and for this we use abstract parabolic theory due to Alexandra Lunardi from her monography from 1995. And we have to prove two important properties. The first one is that cal f depends smoothly on f as a map from hs to hs minus 1. So cal f is nonlinear, fully nonlinear, non-local. So this is not so easy. And then we prove that the problem is parabolic in the sense that the Fresher derivative of cal f at f0 generates an analytic semigroup in this set of bounded operators for all f0 in hs. And this properties identifies the Stokes flow as a parabolic evolution problem, and we can use abstract parabolic theory then to solve the problem. And this is what we are left to do, to prove these two properties, and it all comes back to the to study the properties of the operator BNMO, which I will now introduce. So in fact, we introduce a larger class of operators BNM. So we have here Lipschitz function A from R to R, and we have n linear variables B1, Bn. These are also Lipschitz function first, and here we have the variable h, which is an L2 function, and later on an hs-1 of R function. And on the right, we have the scaling factor 1 over p. We have the principal value integral, and we have this term h of psi minus s over s. And if we forget this term, then this is a Hilbert transform applied to h. Okay, but here we have this additional term. So here we have a product of quotients delta psi s bi over s. Delta psi s of a function u is always u of psi minus u of psi minus s, and we divide by s. And because this function are Lipschitz continuous, this is a bounded function. And in the denominator, we have something similar, 1 plus this delta psi s a over s squared to the power m. It's also a bounded expression. So we have here a bounded kernel, but here we have 1 over s. So if f is 0, this is a Hilbert transform. So if a is 0 and n is 0, then we have the Hilbert transform, as I mentioned. And now let me introduce the operators BNMO of f, because these are the operators which appear in the formulation. And this is simply, these are the operators BNM when f and b1 and bn are all equal to f. So these are operators of this variable h, which is either a 2 function or an sh-1 function. And in the formulation of the Stokes problem, m is always 2. So in the next slides, we will see sometimes instead of m, we have a 2 because previously we had only m equal 2. Yes, let me go back. So you see here 0, 2, 1, 2, 1, 2, 2, 2, 3, 2. And the mapping properties of these operators, there are many mapping properties which are well understood. So for example, if A is Lipschitz and B1, Bn are Lipschitz, then as an operator of the function h is a bounded operator on L2, and its operator norm is bounded by this quantity. Moreover, for S in 3/2, and this is the result obtained jointly with Helmut Abels. So if h in A is in HS and B1 to Bn are in HS, then as a mapping of this function A, we have a bounded operator on HS-1, and its HS operator norm is bounded by this quantity. And now if we come back to the operators BNMO of F, so they are obtained for A, B1, Bn equal F. So they define a map from HS. If f is in HS, then they are operators on HS-1, as we have here. And together with Georg Prokert, we have shown that this mapping is smooth. So, having shown that this mapping is smooth, because these are the operators which appear all over in the formulations, the smoothness of the operator in the evolution equation from HS to HS-1 is a consequence of this property, mainly. And we are left to establish the generator property for the Fresher derivative. So the first step is to compute the Fresher derivative. So we have to differentiate these operators with respect to f. Well, if we take the derivative, so m is 2 here, the Fresher derivative f0 evaluated at f, and h is this additional variable from L2 or HS-1, we obtain this expression. So on the right, we do not no longer have BNMO operators, we have operators in this larger class B and M. And because here we do not have F0, we have an F. Yes, this is a difference. But we can, so take this operator, for example, we can do the following. We can move H in front of the operator and put F on the last position with a prime. And if we do this, we obtain this operator in blue, which is an operator in the class BNMO, evaluated F prime. And this is the leading order part with respect to small f of this operator, because its difference in hs minus 1 is less than a constant, the hs minus norm of h, and the norm of f appears now in hs prime, which is a smaller norm. S prime is between 3/2 and s. So this is the leading order part of this operator. So at the end, the Fresher derivative of a BNMO operator is again a combination of BNMO operators plus some small rest, a low order rest. Okay, for now we have computed the Fresher derivative. If we put for f0, 0, it's easy to see the Fresher derivative is a Fourier multiplier. Namely, we have here a positive minus a positive constant, h composed with differentiation, once differentiation. And this is the square root of minus Laplacian. This is a very nice operator, and one can use very easily Fourier analysis to prove that this operator is an analytic semi-generator. However, if f0 is not 0, the Fresher derivative is no longer a Fourier multiplier, because it's expressed in terms of this singular integral operators BNMO of f0. But in order to prove the generator property, what we do is we localize this operator. So we approximate it by operators, Fourier multipliers of this form. So here we have an alpha, is a positive constant, multiplied with this Fourier multiplier. And we have a constant beta multiplied with d over d psi. And this localization, this is a generalization of the method of freezing the coefficients of elliptic operator, only that now we freeze the kernels of singular integral operators. And then one may use a strategy which I learned from papers from Escher and Escher-Simonet. Joachim Escher was my PhD advisor, to carry over the generator property from this Fourier multiplier. All these Fourier multipliers are generators of analytic semigroup, and then using this their strategy, one can show that also the full operator is a generator. So we are left to localize, to do this localization procedure, and of course this reduces to determining how to localize the singular integral operators, and this is described on the next page. So for the localization, we use so-called epsilon localization families. For each epsilon between 0 and 1, to each epsilon we associate such a localization family. It consists of a finite number of pairs, pi j epsilon, cj epsilon. Pi j epsilon is a function, and cj is a point in the support of pi j. And this function are chosen such that the sum of pi j epsilon square is 1. So this is a partition of unity, the sum over j. This is a finite partition. We have here capital N. This depends on epsilon. The smaller epsilon is, the larger is capital N. And let me say something about this function, pi j epsilon. So if j equal capital N, then the function Pn epsilon squared is a function in red. So this is a function which is 0 between minus 1 over epsilon and 1 over epsilon, and it's 1 immediately after. And for the other j's, the function pj epsilon square are functions which have a support of length epsilon. The support is an interval of length epsilon, so these are these bumps in between. So in between we have this finite number of bumps, and the sum is 1 here. Okay, and then the localization goes as follows. We choose S prime between 3/2 and S, and we are given mu positive. Then, for epsilon sufficiently small, we find such a partition such that pi j epsilon multiple. So this is the operator we want to localize. We want to localize BNMO applied to F0 evaluated at H, and we multiply with pj epsilon. So this is localized by the following Fourier multiplier. So this is a constant, and this is a Hilbert transform evaluated at pi j h. And this is an approximation for this function because the difference in hs minus 1 is less than this arbitrary small constant nu multiplied by the full hs minus norm of pi j h. And here we have a constant k, which may depend on epsilon and could be very large, but here we have a lower norm. Yes, we have the norm hs prime minus 1. And this is true for j less equal n minus 1 and all h in hs minus 1. So this is a result obtained with Helmut Abels, but there are also other results how to localize this operator, where you may have here function a or in front. Maybe one word, how does one see how does this constant appear in front? So this is very easy, because in the definition of these operators, we always have this delta psi s f0 over s, these terms. These appear in the integral. Now, in the localization, they are approximated by f0 prime evaluated at this point psi j epsilon. Yeah, so in the integral, whenever we have such a term, we replace it by f0 prime at psi j epsilon, and then one can prove that this estimate. And here's a theorem about the final result about the localization of the full pressure derivative. So again, nu is positive and given, and s prime is fixed between 3/2 and s. Then, if epsilon is sufficiently small, then we have a constant k which dependent on epsilon, and constants alpha j epsilon which are positive and beta j epsilon in R, such that the pressure derivative evaluated at f multiplied by pi j epsilon minus this Fourier multiplier which I presented you before. So this alpha j and beta j are constants evaluated at pi jf in the hs minus 1 norm is less than this arbitrary small constant nu multiplied by the full norm of pi jf, the hs norm, plus possibly large constant k, but here we have a lower norm of f, the s prime norm of f. And this is true for j between minus n plus 1 and n and all f in hs. And here these constants are uniformly with respect to j and epsilon, always in an interval n at eta 1 over eta. Respectively, this constant beta j epsilon are between minus 1 over eta and 1 over eta, so they are bounded, where eta is some fixed constant between 0 and 1, and eta depends only on f naught, the function where we linearize. And because of these properties, these Fourier multipliers are not only generators of analytic semigroups, but one can prove certain uniform estimates for these operators, and then this is very useful when carrying over the generator property from this Fourier multiplier to the full derivative. So here we are almost done, because we had this problem df over dt equal f of f, and we have shown that this map is smooth with respect to f, and that the pressure derivative is a generator of an analytic semigroup. And then we can use abstract theory from which is due to Alexandra Lunati from her monography from 95 to prove well-posedness and the criteria for global existence. And we have a slight improvement concerning uniqueness of solution compared to the result in her book. And finally, the parabolic smoothing property uses the usual translation invariance of the problem with respect to the horizontal translation via a well-known parameter trick. So that was my last slide. So here are the two papers which I talked about. The first has just appeared, has recently appeared in the Proceedings of the Royal Society of Edinburgh, and the second one is still in the refereeing process, but it's on a good way. So thank you for your attention.